Okay, so two theorems that stem from continuity. Two things we'd like to be able to say based upon knowing that a function is continuous. And the first is, it's kind of a common sense theorem, but it's often referred to and allows us to do a few interesting things, some of which we'll come back to in class before the midterm, and some of which we'll come back to after the midterm. And it's this idea of the intermediate value theorem. You can see hidden up here, this is actually big calculus idea number 5. Continuity, which I didn't write when I was doing the notes earlier, that's big calculus idea number 4, that definition for continuity that I gave you. Right, so big calculus idea number 5 is the intermediate value theorem. And you can read the definition. It says, suppose that a function is continuous on a closed interval. We just talked about what that means. And let m be any number, okay, between the height of a and the height of b. So m is a height. And if we look at the diagram down here, we can say, okay, there's m. Then there exists a number c such that if c falls between a and b, and the height at c equals m. Essentially what we're saying is that if we pick two values along a curve, here's a and here's b, and we pick a height, m, that falls between the height at a and the height at b, if the graph is continuous, there must be some value, right, some x value we can plug into the graph. In this case, it looks like there's 3 x values, such that we get out m. Because continuity means in order to go from the height at a to the height at b, we're going to have to hit every height in between along the path. So the intermediate value theorem is a statement of that. It's a statement of truth. And it should be somewhat common sense if we really understand what it means for a function to be continuous and what relationship heights have to one another on a function. Okay, so what do we do with that? Well, let's say that I wanted to show that there's a root of this function, 4x cubed minus 6x squared plus 3x minus 2 equals 0, in the closed interval 1 and 2. Well, that means that I'm looking for c between 1 and 2. And what c, the actual height of c, is going to be equal to 0. Now, the intermediate value theorem doesn't tell us what that height is. It just tells us that it exists. Okay, now, I could go about solving this function directly. I could try to factor it, or it looks like I could probably, and well, maybe we'll do this in a second. It looks like I could group this and figure out what number that I'm looking for. But ultimately, what we should realize is that the intermediate value theorem just tells us such a place exists. And what we do is say, well, if c is between 1 and 2, then I want to know what f of 2 and what f of 1 is. So f of 2 is going to be 4 times 8 minus 6 times 4 plus 6 minus 2, which is 32 minus 24, which is 8 plus 16. This is going to be 12. And f of 1 is going to be 4 minus 6 plus 3 minus 2, which is minus 1. Now, why does this guarantee that there's a root in between? Well, if I know that at 2 I'm at a height of 12, and I'm at 1 I'm at a height of minus 1, there's only 2 ways to do that. The first is that I have to go directly from minus 1 to 12 on the graph, whatever that is, right? Here's minus 1, here's 12. The only other way this could happen is if I jumped, right? If I was suddenly going along, I'm like, okay, here's minus 1, and then I start up again at 12. I jump later on. But we happen to know that's not the case because we know the function that we're talking about, which is a polynomial, is continuous everywhere. We know that polynomials don't have any discontinuities. So that guarantees the existence of a root between 1 and 2. Okay. Alright, let's look at a second theorem. This one's actually one of my favorite theorems. This is big calculus idea number 6. And we call it the squeeze theorem. It's hidden in this tiny bubble up here. It's also called the sandwich theorem, but that's not as interesting. So, this is our squeeze theorem. And keep that in mind. The word in this case is actually appropriate for what the theorem does, which isn't always the case in mathematics. But this word, the idea of squeeze, is exactly what gives us the answer we're looking for out of this theorem. So, we say let g of x be less than or equal to f of x, which is less than or equal to h of x, for all x in some interval, including c, except perhaps at c. All right, so we say, all right, we're going to line three functions up in terms of height. Right, that over a set, right, I'm going to have, well, this isn't what it's going to look like, but here's something that satisfies that value, right? G of x. Right, one function under the other. But that's not really interesting. We would know what the limits are in those cases. We say, okay, well, if I happen to know that the limit as x approaches c of g of x is the same as the limit as x approaches c of h of x, right, if they had come to the same value, then I can assume that the middle function, right, gets squeezed between the two. It also has to approach L. Because I know that it falls between g of x and h of x in the interval that I care about. Right? And if the two ends of the interval, those two, if the above and below function go to L, then the middle function must go to L. Again, this is something that's pretty common sense, but it actually ends up giving us an important result that we're going to need for class tomorrow. So let's take a look at an example of what that would look like. So if I want to do the limit as x approaches 0 of x squared times sine of 1 over x. Algebraically, if I plugged it in, I would get 0 times sine of 1 over 0, and we kind of know that sine of 1 over 0, we're talking about something like sine of infinity, and we're not really sure what that is. Right, so that's a question that at the moment we're not really sure how to answer. We'll get there, but at the moment we're not entirely sure how to handle that. Right, so maybe there's another way to do this problem using the squeeze theorem. Right, well, in order to use the squeeze theorem, the first thing I need to do is find this idea of g of x less than or equal to f of x less than or equal to h of x. And we need to find this relationship between the functions. Well, let's just start with that piece sine of 1 over x, because that's the piece that's causing issues. Right? I can make a claim, and I happen to know something about the heights of sine. I know that they're going to be between -1 and 1. Now, that's not entirely whole entire function, right? But I could go ahead and multiply everything through by x squared. Now, we always have to be careful when multiplying through by a number, right? When I'm doing inequalities, I have to make sure I'm not changing the value of the expression. But x squared is always positive, so I don't have to worry about changing the value or the order of the inequalities for this problem. So now I actually have what I'm looking for. I have an f of x, a g of x, an h of x. Right? They're in order. It will always be the case that minus x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared for a particular interval. And we'll see that graphically in a second, what that looks like. Actually, let me jump down and show you that. Right? So if we look at it graphically, here are those three functions related to one another. You can see that the blue is x squared, and the red is minus x squared, and the tan in the middle is x squared sine 1 over x. What you notice is that it actually doesn't turn out to be the case forever, right? That one of these functions is always, that they're always in that order. But I can pick an interval here in the middle, right, where that order seems to hold true. Right? Where as long as there's some interval that I can pick where they stay, right, in that order, right, minus x squared less than or equal to x squared sine 1 over x less than or equal to x squared, I can execute the squeeze theorem. And it's not very difficult to execute. I'm just going to think about the limit as x approaches 0 of all the pieces. So now I just think about the limit of all the pieces together. Now, what I'm doing here is I'm not really applying the limit like it's an operation. I'm really writing a different expression. Okay? This isn't really an operation in the problem. We don't think of applying the limit to something like we do adding or subtracting. But when I plug in 0 now and solve those limits, I get 0 on one end. And I don't know what happens in the middle. And that was the whole idea, is I don't really know what happens in the middle, but I get 0 on the other end. And the only option I have by the rules of inequality are that the limit as x approaches 0 of x squared sine 1 over x must be equal to 0. It's squeezed in between those two functions that it falls between. So it's a somewhat roundabout way to get to the answer, but it helps us answer a couple questions that we didn't have access to before.